Typically, steam causes more severe burns than hot water, but a chef can place his hand over the steam escaping from a pressure cooker. This means that the steam that has escaped from the pressure cooker is not too hot. So what makes this steam cool down? Meet me in the studio and you'll find out. Hello and welcome to another episode of Physics with me, Chandralekha. All of us see thermodynamic processes at work all around us, whether it's heating water or cooking food or even when you exercise. And thermodynamic processes is what we are going to discuss today. In today's episode, we'll look at specific heat capacity and molar specific heat capacity, define thermodynamic state variables, understand various thermodynamic processes and their applications. And we end the session with Exam Decoded, where we tell you all that you need to know about cracking those exams. Let me ask you something. What happens when heat is supplied to any substance? Yes, you guessed it right. From first law of thermodynamics, delta U is equal to delta Q minus delta W. So heat supplied can increase the internal energy of the system and or work is done by the system. Let's focus on the case where an amount of heat delta Q supplied to a substance increases its internal energy and leads to an increase in its temperature from T to T plus delta T. Recall that heat supplied to change the temperature delta Q is equal to the product of the mass m times the specific heat capacity C times the change in temperature delta T. Note that C is equal to delta Q divided by m delta T. So the SI unit of specific heat capacity C is joules per kg per Kelvin. Since delta Q is measured in joules, mass in kilogram and delta T in Kelvin. A more convenient way to express mass is in number of moles of a substance rather than in kilograms. Consequently, the expression delta Q equals mc delta T can be written as N capital C delta T. Here, N denotes the number of moles. Note that instead of a lowercase c, capital C is used in this expression for molar specific heat capacity, and its unit is joules per mole per Kelvin. As you can guess from dimensional analysis, let's focus on molar specific heat capacities of gases. When we talk about gases, the molar specific heat capacities are of two types, one at constant pressure, Cp, and another at constant volume, Cv. Before I proceed any further, I believe one of you has a question for me. Let's hear it out.
Hello ma'am, which one of the two will be greater? Molar specific heat at constant pressure Cp or molar specific heat at constant volume Cv, and why?
Great question. The student wants to know which one of the two will be greater, molar specific heat at constant pressure Cp or molar specific heat at constant volume Cv, and why? Well, the difference between Cp and Cv can be calculated from an experiment. Heat delta Q is supplied to raise the temperature of an ideal gas from an initial temperature Ti to a final temperature Tf. Let's do two experiments, one at constant pressure and the other one at constant volume. Remember, from the first law of thermodynamics, the heat supplied, delta Q, is equal to the change in internal energy, delta U, plus the work done by the system, delta W. Note that molar specific heat capacity of ideal gas is the heat required to change the temperature of 1 mole of a gas by 1 Kelvin. and cause a corresponding change in the internal energy, delta U, since the change in temperature is directly proportional to the change in internal energy. The question is all heat supplied used to increase the internal energy of the gas and hence its temperature, or is some of the heat used to do work by the system? When we supply heat at constant pressure, some of the heat is used to do work, and some heat is used to change the internal energy, and hence the temperature of the system. When the heat is supplied at constant pressure, the work done is given by the product of pressure times the change in volume. Hence, from first law, heat required delta Q equals delta U plus P delta V. But if the volume is constant, then change in volume or delta V is zero. So, there's never any work done in a constant volume process. This implies that all the heat supplied will increase the internal energy of the system, and delta U will be equal to delta Q in a constant volume process. Remember, delta U is proportional to the change in temperature. So to cause the same change in temperature, more heat must be supplied to the gas at constant pressure than the gas at constant volume. Since at constant pressure, part of the heat is used to do work rather than only change the temperature. So, Cp must be greater than Cv. Well, for an ideal gas, Cp minus Cv is equal to gas constant R. Because the work done at constant pressure, delta W, is equal to P delta V, which is equal to nR delta T from the ideal gas law. For 1 mole of gas, N is equal to 1. And for delta T is equal to 1 Kelvin, the heat required for this work done at constant pressure is R. This is the extra contribution to Cp, which is not there for Cv due to the fact that some heat supplied is used to do work at constant pressure in addition to the heat required at both constant volume and constant pressure to change the temperature. Hence, Cp minus Cv must be equal to R for ideal gas. Now let's look at a question posted on our website by Tanya. Here's the question. Consider a gas chamber which is connected to a vacuum chamber. This system is insulated from the surrounding. Both chambers are interconnected by opening a hole between them, and gas flows into the vacuum enclosure. The gas is at an initial temperature T1 and pressure P1. We find that the final pressure is P2, but the temperature stays T1. Why does this happen? You think about it while I'll take a short break. But don't go anywhere, because when we get back, we'll discuss the answer and much more. Stay tuned.